Okay, so today we will talk about branch and price. Recall I said in solving global optimization problems, uh, there are two building blocks. One is branching, right, spatial branching. The other is coming up with tight convex relaxations. In the previous lecture, we discussed a few different convex relaxations, especially for quadratic problems, right? Recall that you could use McCormick relaxation, semi-definite programming relaxation, and so forth, right? And for composite nonlinear programming problem, you could refactor them into univariate nonlinear functions and come up with a convex relaxation for each of these univariate functions. Now, after we have discussed convex relaxations, then we can use them in a branch and bound method, right? So the branch and bound method for solving non-convex optimization problem is called branch and reduced. Branching, you already know what branching means, and reduce means range reduction. We will talk about range reduction in this lecture. Okay, so again, just an overview of the so-called spatial branch and bound method, right? Because we have continuous variables, then we may branch on the continuous domain, right? So here, just to refresh your memories, if you have a non-convex function P, you can come up with a convex relaxation R, right? And then the convex relaxation still has a gap compared with the original function. Then what you would do is dividing the domain of the non-convex functions into two parts, and then you come up with two separate convex relaxations that are hopefully tighter than the original convex relaxation. Right? As you can imagine, if you keep branching as the diameter of this interval goes to 0, then the convex relaxation will approach the original non-convex function. So you can check this is true for many of the convex relaxation we discussed in the previous lecture. For example, McCormick relaxation. If you have upper and lower bound close to each other, then the McCormick will approach the original non-convex function. Okay. So what does branch and reduce mean? It was first proposed by Rao and Sachnidis in their seminal paper called a branch and reduce method for global optimization. So this is used as the basis of the global optimization solver called Baron. Right? If you took my lecture a year ago, Groovy still cannot handle general non-convex nonlinear problems. So one of the pioneers in this area is Professor Nick Sachnidis, who is also a chemical engineer. He developed one of the earliest solvers for solving global optimization problems. Now, you may wonder what's the difference between branch and reduce and branch and bound itself, right? So compared with branch and bound for MILP, I would say branch and reduce has two major differences. The first difference is quite obvious because you may branch on some of the continuous variable. In branch and bound for mixed integer linear programming problem, we only branch on the binary variables. So the second difference is what we will focus on today, called range reduction or bound tightening. So the idea of range reduction or bound tightening is to reduce the range of the variable bounds. Okay, so again, why do we want to reduce the range of the variable bound? The main reason is because if you look at any convex relaxation, for example, this McCormick envelope here, right? Imagine the range of the variable is reduced to a very narrow range, close to 0, right? Then this convex envelope will be arbitrarily close to the non-convex nonlinear function, right? So if the range is large, then your convex relaxation is weak. If the range is small, then the convex relaxation gives you a tighter bound, right? So it's a same idea we expressed in the first slide, where if you can reduce the range of the binary of the continuous variable, then the relaxation R2 you come up with will be tighter than the original relaxation you come up with using a wider variable range, right? And this is applicable for most of the convex relaxations we talked about in the previous lecture. You can go back and check if it works, right? So because this is an important concept, let's think about one more example to check. Other than the McCormick envelope, let's check another envelope to see whether range reduction can help tighten the convex relaxation, right? So remember the other commonly used envelope we talked about in the previous lecture is the envelope for concave functions, right? So let's say if you have f of x equals to log of x, right? It looks something like right. So this is a concave function. Now, if the variable range is xl and xu, suppose this is a quite big range, then the convex envelope you come up with is essentially the line segment between this range, right? And supposedly you did some range reduction and narrow the range to this very small interval here, right? After some range reduction, and we will talk about range reduction algorithm in this lecture, right? Now, intuitively, this purple line segment is much closer to the concave function than the original large range, right? So there are also some theory related to how fast will the error converge, right? How fast will the error goes to zero as the diameter of the range goes to zero, right? Some of the relaxation have, like say, first order convergence, some have second order convergence. There is a rich theory on that. But intuitively, you can believe me, why we want to do range reduction is because if you can tighten the range, then you will have a convex relaxation closer to the non-convex function, then you can converge faster. Right? That's the reason we want to do range reduction. Okay. Now, before we give you the pseudocode for branch and reduce algorithm, we will talk about a few heuristics. Right? So remember in branch and bound, there are a few decisions you need to make, including among all the active nodes, which node are you going to pick to branch, right? So this is called the node selection rule, right? So typically in solving non-convex problem, we will use a heuristic rule saying best bound first, right? So that you will select the node with the smallest lower bound, right? Or the smallest convex relaxation, right? Because at that particular node, you can improve the lower bound, right? Because if you want to improve the lower bound, you must improve the lower bound on the node that gives you the smallest lower bound. So that's why we use this particular node selection rule. What about branching rule? Okay. So does anyone still remember in mixed integer linear programs, what are the branching rules we've talked about? Maybe max fraction, right? So that's a good heuristic. You branch on the binary variable that are closest to 0.5, right? Okay. What are the other branching rules we talk about?
Strong branching.
Yeah, so strong branching, right? Strong branching means you tentatively branch on each of the fractional binary variable and check which one give you the best bound improvement. Okay, that's just a refresh your memory, okay? Now, we could use some similar philosophy in branching on continuous variables, okay? Now, if you are solving general nonlinear non-convex problem with some binary variable, typically you will branch on the binary variable first before you branch on the continuous variable. That's sort of the heuristic, because usually the binary variable represents logic, the continuous variable represents some physical quantity. Therefore, you would branch on the binary variable first using the branching rule we covered in MILP. Okay. And what about the continuous variable? So one of the heuristic to use is to select a variable with the largest underestimating gap. Okay. And then occasionally you will select variables corresponding to the largest range. Okay, so the first branching rule is about how far you are from satisfying the nonlinear non-convex constraint. It's not so trivial to say that in math, but intuitively, the idea is you have a convex relaxation, then the convex relaxation may not satisfy the original non-convex constraint, right? So then you will assign to each variable how much non-convex constraint is each variable violating. It's not a trivial procedure. We will not talk about this in detail, but you can assume there is a mechanism where you could sort of measure the mismatch between the convex relaxation and the original non-convex problem and attribute that to each of the variable, right? And then you will select a variable that gives you the largest violation in the non-convex constraint. And occasionally you probably want to select a variable with the largest range. So why would you want to? The second branching rule is easy to check, right? You check the upper and lower bound of each variable, and then you will pick the variable with the largest range. Okay. So now let me ask you a quick question. Why would the second branching rule, the largest range branching rule, make sense?
That we will have a much better estimation when we split it, as you just showed before.
Yeah, right. So it's similar to what I showed in this figure, right? If you branch on the range of a continuous variable, you can improve the convex relaxation. Right? As the diameter of each of the variable goes to 0, you will have a 0 error, right? So therefore, you would, from time to time, pick the variable with the largest range, right? So if you always split the variable with the largest range, the max diameter over the variable will always be decreasing. At the end of the day, all the diameters, all the ranges will be decreasing, right? If you keep selecting the variable with the largest range. Okay, and then the branching point selection, typically we just branch at the midpoint of the interval, right? Just like again, in this figure, you have an original range, and then you split at the midpoint of this range, such that the convex relaxation at both the left and the right interval can be improved. Okay. What about convex relaxations? If you look at the document of modern MINLP solvers like Barron or Gurubi, they mostly use linear programming relaxations. Right? But then they can add cutting planes that are derived from some nonlinear relaxation, like semi-definite programming. Again, like last time, we talked about how do you derive a linear cut from a semi-definite programming relaxation. Right? It's essentially, you need to add a cut looks like V transpose X, V greater than or equal to 0, where V correspond to the eigenvector with the smallest eigenvalue, right? Okay. So that's why you could derive linear cuts, right? Using SBDP relaxation. Before we go to the pseudocode, let's see any conceptual questions here. Okay. Now let's go over the pseudocode of the branch and reduced algorithm. Right? Before that, you can sort of refresh your memory what we did in branch and bound for mixed integer linear programming. Right? You have a bunch of active nodes. Right? At the beginning, you solve the root node relaxation, right? And then you pick a node and try to get the upper lower bound. And according to some branching rule, you will branch on one of the variables, and you create two new nodes until there are no active nodes. During this branch and bound procedure, there are two ways you could fathom the node, right? One is fathom by optimality, Right? If the lower bound is even worse than your incumbent solution, there is no way you could get even better solution on this particular node, right? Oh yeah, this is fathom by bound. The other is fathom by optimality. If the upper and lower bound agree with each other on a particular node, you can fathom a node by optimality. Okay, so same ideas can be used here, except that in branch and reduced, you will need to do some bound tightening, right? Because I said, if the variable bounds gets closer, then you get better convex relaxation, right? So therefore, in branch and reduced algorithm, quite some computational time is spent on tightening variable bounds. Right? So remember, in mixed integer linear programming, most of the times are probably spent on solving the linear programming or adding cutting planes. Right? So those are the times spent. But in a branch and reduced algorithm, a significant chunk of time is spent on tightening the variable bounds. Right? It probably you will spend more time tightening variable bounds than solving the relaxation itself. So that's a major difference here. Okay. Otherwise, the procedure is almost identical to branch and bound in mixed integer linear program. Okay. Now, let's say we start the algorithm where you put the range as, let's say you start with the original range of the variables. Again, another thing to keep in mind is when you solve non-convex problem, so a side note here is you should specify bounds for all the variables if you are solving non-convex optimization problem using a global solver. Okay, so if you want to remember only one thing from this lecture, this is the line of sentence to remember. Okay, even if you don't know how to do range reduction from an algorithmic point of view, doesn't matter, the solver will do that for you. Right? But if you want to just interested in solving practical problem, and then this is a takeaway from this lecture. Right? So if you want to solve any non-convex, nonlinear problems to global optimality, make sure you specify bounds for all the variables. And those bounds should be as tight as possible. Why that is the case? Because tighter variable bounds give you tighter convex relaxations. Right? That's one thing to remember. Right? If you don't remember any of the algorithm, it's actually okay. Right? But typically, if I work with especially undergrad student or master students, then they come up with a problem and then say, this problem does not solve, right? Usually 99% of the instances is because they didn't specify variable bounds for some of the variable, or for some of the variable they specify some trivial variable bounds. Okay, so this is one thing to remember. Okay, so let's suppose you specify variable bounds already, and then you could start with the range, right? This range of variable you specify to start the branch and reduce algorithm. Okay, and you enter the main loop of this this algorithm. Of course, you would keep updating the upper bound and the lower bound, right? The lower bound is the convex relaxation. So suppose we are minimizing, right? And then the lower bound should always be the minimum of all the active nodes, right? So because that's the definition of the lower bound. Then you could take the node. Okay, yeah, so this step is pruned by bound, right? For all the nodes whose lower bound is even worse than the current upper bound, then you can fathom those nodes, right? This is called prune by bound. And if the number of active node is empty, then the current solution is optimal since you have already pruned all the nodes. So then you go to the next iteration. Okay. So step 2 is subproblem selection. You will select a node from the set of active nodes according to some node selection rule. Typically, we use the node selection rule as we select a node with the smallest lower bound or the best lower bound for it. And step 3 is tighten variable bounds using things like feasibility-based range reduction. You don't know what that is yet. I will talk about that. Okay, so first you select a node, then you will try to tighten the variable bounds for that node. Okay. So how do we bound the node? The lower bound is just solving the convex relaxation. Right? So if the convex relaxation is infeasible, then this node is infeasible because it overestimates the feasible region. Now, if the solution of the relaxation is found and is feasible to the original problem, that means you find a solution that is feasible for the original problem. Then if the solution is even smaller than the current upper bound, the current feasible solution, then you can update the current solution. Right? It's just like in branch and bound. You find a feasible solution, you will check if it is better than your current best feasible solution. If so, you update that. Okay, and then you could make xi the current best solution. Right? Otherwise, if the lower bound is even worse than the current best solution, then you can fathom the node by bound and go back. Okay. Otherwise, you go to step 5. So that means you haven't. If you go to step 5, that means you have not been able to fathom the node by bound or by optimality. Then you probably want to spend more time on this particular node, right? So by spending more time, one option is you can try to improve the upper bound using some heuristic. A heuristic can be you solve the problem using a local solver. You could also do some post-processing by further strengthening the bound using range reduction. So this step is the major difference compared with mixed integer linear programming, right? So in mixed integer linear programming, you solve the linear programming relaxation, and then you cannot fathom the node. Then you will just go ahead and do branching, right? But in global optimization, you will still be able to do some post-processing to hopefully further tighten the relaxation, right? So the post-processing is pretty much range reduction, right? You want to further tighten the variable bounds to see if you can get further improvement, okay? So if the range reduction was successful, meaning that at least one variable is tightened by a pre-specified amount, then you will reconstruct and go back to resolve the problem. And so you will iterate back and forth to try to tighten the variable bounds, right? And if you find the bounds cannot be improved, then you will go to the branching step, right? So therefore, you will keep tighten variable bounds, solving the relaxation, tighten the variable bounds until you find you cannot improve the problem anymore. Then you will do some sort of branching. Typically, we will just cut the range of one of the variables by half, right? We will cut at the middle point. Okay. So you could go back to read the details of this pseudocode, right? As long as you kind of get the high-level idea, it is fine, right? The high-level idea is you will select a variable to branch at some point, right? By dividing them into two nodes, then you get a tighter convex relaxation. And in the meantime, you are also doing reduce, right? Means range reduction, right? So we will talk about range reduction later on, right? So basically, both branch and reduce have exactly the same goal, right? They want to tighten variable bounds, right? By branching, you are dividing the length of the interval into two intervals, right? So then you tighten the variable bounds. Then there are also other ways called reduce. Reduce is some other techniques to tighten variable bounds, right? Again, the motivation is to tighten the convex relaxation at the end. Okay. Now, an interesting question to ask is, does spatial branch and bound converge? Okay, so let's think a little bit about that. First of all, why would branch and bound converge for mixed integer linear programming problem?
Finite number of nodes.
Yeah, right. So you have finite number of nodes because there are only finite ways to branching the problem. In the worst case, you will branch 2 raised to the power of n nodes, right? By enumerating all the combination of the binary variable, but branching is finite, right? In spatial branch and bound, is the number of branching steps finite? No, because you are branching on continuous variables, right? Although theoretically, as the number of nodes goes to infinity, or you will have the diameter of each variable being 0, then that convex relaxation will converge to the non-convex problem. But no one will solve a problem using infinite number of nodes, right? Okay, so therefore, what type of theoretical properties can you prove for spatial branch and bound? Right? So usually the property you can prove is convergence in the limit, right? Meaning that if you let the number of iterations go to infinity, it will converge to the original non-convex problem, right? The other convergence you can prove is that I gave you a tolerance of epsilon, right? Maybe a tolerance of 0.1% gap. Then you can show for this finite tolerance, I can converge in a finite number of steps. Okay, so there is no way you can show you get 0 gap in a finite number of steps because it's not a finite algorithm because of the continuous variables. Okay, so we will not show a rigorous proof. If you want to have some interesting reading, you can check this global optimization book by Haas and Tui in the reference. Okay, so in summary, in order to have finite convergence, if you set a given tolerance, in order to have a finite convergence, you need the first 2 properties. And these 2 properties can be quite intuitive. Okay, consistent partition means any open partition can be further refined. As the refinement progresses, the lower bound converges to the non-convex problem value, right? So especially the key is this part, right? The lower bound converges to the non-convex problem value, right? That is the assumption I made before I introduced the algorithm, right? When you, if you look at the relaxation we draw here, right? If you keep partitioning the problem, the convex relaxation will converge to the non-convex function in the limit, right? But if you don't have this property, let's say even if you have a 0 interval, you still have a gap, then this algorithm will not be able to converge, right? So the algorithm will be able to converge is under assumption if you keep partitioning and you get very small intervals whose diameter goes to 0, then your non-convex, then your convex relaxation will be exactly the non-convex function value, right? So that's sort of the intuition why you need consistent partitioning. Okay, besides that, you need bound improving node selection rule. Every finite number of steps, a node with the least lower bound is selected in your node selection rule. This is quite intuitive because if you want to improve the bound, you need to improve the best lower bound from time to time, right? So that's why you need this node selection rule. Another property is so-called exhaustive, but it's an optional property, but it's good to have, right? So it says the limit of the diameter of the sequence of nested partition is 0, right? So that means the diameter of the interval goes to 0, right? It's not necessary for convergence, but most of the branch and bound algorithms satisfy that. Because from time to time, you will select the node, select a variable with the largest diameter. Okay, so that's that here. Now, the rest of this lecture will be on range reduction of bound tightening. In most of the literature, people will refer to it as bound tightening instead of range reduction. But then in the branch and reduce algorithm, they refer to it as range reduction. So I will just use bound tightening from now on. Okay. So why do we want to do bound tightening again? It's because the smaller the variable domain, the faster the branch and bound converges, right? If you have tighter lower bound, you can converge in fewer number of nodes. So we will talk about 4 different algorithms for bound tightening. One is based on marginals or based on the dual variables. Then we will talk about 2 very intuitive methods called feasibility-based bound tightening and optimality-based bound tightening. The third approach we will cover is based on probing. Okay. Now let's start with marginal-based range reduction. So this is the most, let's say, the most theoretical bound tightening method I will cover in this lecture, right? So that's why I put it first. Otherwise, if I put it at the last one, then people will already fall asleep at the end, right? So this is the hardest one. The other 3 methods are very intuitive, okay? And I also want to use this problem to show you a very interesting property of convex optimization problems, okay? So now before we show the proof, I will show you the claim of this range reduction approach and show you a geometric intuition of this approach. Okay. So if you don't want, if I'm not interested in the math, you can just look at this picture, and that gives you a very interesting geometric intuition. Okay. Yeah. So the idea is the following. Okay. Suppose we have a convex relaxation solved at the given node. Right? So suppose the convex relaxation looks like this. C transpose X subject to Gi of X less than equal to Bi, right? Because I said it's a convex relaxation, then Gi is convex, right? Typically, you can assume Gi is a linear function, right? Since most of the time we are using linear programming relaxation. Okay. Now, suppose at the optimal solution of this convex relaxation, one of the constraint is active. Right? So that means at the optimal solution of this convex relaxation, this less than equal to inequality holds true, right? You have an equality, right, at the active solution. Now let's suppose the corresponding dual multiplier is lambda j star. Okay, and lambda j star is greater than 0. Okay, so and then I claim I can tighten the bounds of this constraint. Right? Remember this bj, bi, each of the bi or this particular bj gives an upper bound of this constraint. Right? So this claim is saying that I can improve the lower bound of this constraint if this particular constraint is active at the optimal solution. Right? So I can improve the constraint by u minus L divided by lambda j star, where, again, u is the upper bound. Right? The upper bound corresponding to a feasible solution. And L is the lower bound I find at this particular node. Right? So in other words, L is the optimal solution of this convex relaxation. Right? So if you solve this particular convex relaxation, it is a lower bound of this particular node. Right? So L is a lower bound, and U is the best feasible solution I found so far. Right? Okay. Now, what does that mean? Right? That means originally you have this less than equal to constraint. Right? So now I said if you are aiming to find a better solution than the current solution you find, then there does not exist any solution who is less than equal to this particular value. So therefore, you can set gi of x to be greater than equal to this value here. Okay, so let's give you some time to try to absorb this conclusion first and see if people have any questions. Any questions or? Yeah.
Whenever we say, I guess, dual multiplier, is that referring to like the same thing as whenever we're taking like Lagrangian duals?
Yeah, exactly. So you can think about the dual multiplier as assume you solve this problem using primal dual interior point methods, and the lambda is the optimal dual to this convex problem. Or if you solve a linear program, it is the dual for that linear programming problem. Okay, yeah. Yes?
So when we're solving g of x,
Yeah.
or when we're trying to, we're not solving g of x, when we're trying to minimize the ct of x,
Yeah.
Do we already know our u and l, or which parts of those, is the u or l what
Yeah.
we're changing in order to actually
Right.
solve that minimization?
Right, yeah, that's a good point. So let's say the U is something you already know. Maybe you'll find some good solution in other nodes or this node. Doesn't matter. It's just the best feasible solution you'll find so
So
far.
it's your best feasible solution so far?
Yeah, so far, yeah.
And then you're minimizing it, changes our lower bounds
Yeah,
to give you either the same. 'Cause
Right.
If u and l are equal, then you're there.
yeah. So
Okay, so it's either gonna be the same or better.
right. So now if your U must be greater than or equal to L, right? Otherwise you converge already. Right, yeah, okay. So here your U is strictly greater than L, where L is, you can think about L as the solution to this convex relaxation because it's a relaxation, it gives you a lower bound. Okay. Yeah, so this essentially is saying that originally this relaxation is gi of x less than or equal to bi, right? So what this tightening is saying, it is guaranteed if you want to find solutions better than u, your g of x also has a lower bound of this number. Okay, yeah. So why that is the case, we can look at this particular picture to give you some sort of intuition, right? Now, you can think about xu as, this is not the best label here. We could change this label to, let's say, bj, right? Okay, so let's change this to bj here. Okay, so let's assume at the current convex relaxation, your right-hand side for that particular constraint is bj. And then this is a non-convex function, the original non-convex function, right? And then this blue line is this convex relaxation generated by this particular problem. Suppose it is a convex, but of course it's a constraint optimization problem. It's not as simple as this, but intuitively you can imagine this is a relaxation at this particular node, and then this is your original non-convex problem. And the blue curve always underestimate the red curve here. Now, when the right-hand side equals to bj, you can think about the lower bound you get is here. Okay, so this is the lower bound you find so far. Now, if you perturb the right-hand side, right, then the bound you get will change, right? If you change bj, this number here, then the bounds you get will also change. So if you move it too far, then if you move it too far until this point, maybe the lower bound you get will already be worse than the upper bound, right? So therefore, you are not interested in this part where the relaxation already give you bound that are greater than equal to u, right? Okay, so why you could draw this particular line here? It is because we can show using the optimal dual variables, you can get a so-called linear underestimator of the convex relaxation. Okay. That's sort of the intuition here. Okay. Now, hopefully you are not too confused. This is sort of a geometric intuition, but then I will show you a mathematical reasoning of the problem. Okay. So maybe let's show it mathematically, and then we come back to this particular slide again. Now, in order to show it, I would like to show you a property of a convex optimization problem we haven't shown before in previous lecture. Okay, so this is a side note independent of this particular problem. So just a side note in order to show this. In order to show this claim here. Now, let me introduce a concept called value function of an optimization problem. So let's define this value function as VU, which is a minimization problem over X, C transpose X, subject to GX less than equal to U, right? So we assume they are, let's say, M constraints. In other words, G is a function from Rn to Rm, right? They are in total M constraints, and U is a parameter in Rm. Okay, so this function V of U is a very general definition. It is called a value function of an optimization problem. Okay, so you can interpret as this, right? So the parameter U is like the right-hand side of this convex optimization problem, right? So give an arbitrary value of U, right? In order to evaluate the function VU, you need to solve an optimization problem that involves variable X, okay? Yeah, so now if I set let's say U equals to B, right? So essentially, if you want to evaluate this value function at value B, that is nothing but the original convex relaxation problem you solve, right? So this value function is describing if I can perturb the right-hand side B to any arbitrary value, how will this optimization problem's objective value change? Okay. So in order to get the value of VU, each time you give a different variable U, you need to solve an optimization problem that involves X, right? So it is not an explicit function, right? To evaluate this function, you need to solve an optimization problem. Okay. Now, there are a lot of literature related to what property this value function have. Right? right? Is this function convex? Is it differentiable? If it's differentiable, can you give a gradient of this function, right? Okay. So this value function I plot, I define is essentially this blue curve I draw here, right? When you are changing the right-hand side of the parameter, how will these convex relaxations objective value change? That's what this blue curve I define here. Okay. Now, a claim here is so VU I think VU is a convex function, and then we can find a subgradient right. So a subgradient means if you have a function here, right, so if you have a differentiable function, it is easy to find a gradient, right, because it's differentiable. But then if you have a function that is non-differentiable, like an absolute value type of function, right, at this particular point, the gradient does not exist, right? The subgradient means you can find an underestimator a linear underestimator of this function, right? So there are infinite number of linear underestimator of this function, right? This is one. You can find infinite number of linear underestimator of this function, right? So in this case, we will show that there is a particular subgradient of this function VU at a given point B. Okay. So that's something we will show that here. In other words, let me check the conclusion here. Lambda, okay. So we will show VU greater than or equal to AB minus lambda star. So we will show that the optimal dual solution okay. So this is something we will show next, which is here's your value function defined with respect to an optimization problem, right? When you change U, this value function will change. Okay, so we will show that at a given particular point, U equals to B, right? At U equals to B, lambda star is the optimal dual at U equals to B, and then minus lambda star will be a subgradient at this particular point B. Okay, so this is a definition of the subgradient. Basically, at a particular point B, your VU function is underestimated by this linear function of U, right? Okay, so you may remember this as a first order characterization of a convex function, right? If you have a convex function, you linearize at a particular point using first order Taylor series expansion. Then it underestimates the convex function, right? Just like in this particular case, at this particular point, you draw the first order Taylor series expansion, it underestimates the convex function, right? But in this case, the function VU may not be a differentiable function, right? So it may be a function like this, and then what you can get is like a subgradient of this function. There are infinite number of subgradient. What we will show is this minus lambda star is one of the subgradient of this particular function, okay? Is this claim clear? It can be quite counterintuitive the first time you've seen this definition of value function.
Why do you give a lower bound?
Why we gave a lower bound of this?
So V of U is the value where these lines are intersecting.
Yeah,
Where you have infinite gradient.
yeah.
So
Yeah, so basically if the function is convex, you are interested in the subgradient, right? Because you can under-approximate a convex function. If a function is concave, it's the other way around, you want to give an upper bound, okay? Because this, you can show this function VU is a convex function, right? As the right-hand side of this optimization problem change, the value function will change as a convex function, okay? So that's why we want to give a lower bound, yeah.
So is that equation the V of B minus lambda U minus B?
Yeah.
Is that the equation of the line that's intersecting right there?
Right. So if you plug into U equals to B on the right hand side, right? It is this part will be 0 at U equals to B. Then you get VB equals to greater than or equal to VB. Right? But of course, if you change away from B, the right hand side is like a linear function that underestimate V of U. Right? Like while you can imagine this red curve is a value function, and then this right-hand side is like one of these black function that underestimate that. Yeah, it's one of those lines. Yeah. Okay. Yeah. So we just show minus lambda star represent one of those lines. Right? But there are others. It is not so easy to find. Okay. Yeah. Now let's show why this is true. Okay. Now, let me open a new page. Okay. So because this is a convex problem, we know strong duality hold, right? I assume the original problem is a convex problem. Then you can show, let's define the Lagrangian dual function of this problem, right? Let's say this is parameterized by U, and then the Lagrangian function is minimize x C transpose x plus, so we should write it in terms of dual variable. So let's say lambda is the dual variable at a given value U, okay? So this is nothing but the Lagrangian function, right? Where lambda is greater than or equal to 0. Okay, so by definition, maybe before this, let's write, So the value function V of U is nothing but max over lambda greater than or equal to U d lambda U, right? This is because of strong duality, right? Because I assume G is convex. Now, VU is the value function of the primal problem, right? And d lambda U is the dual problem, right? So for convex function, primal equals to dual, right? Now, here, since I'm maximizing over lambda, right? So all the lambda greater than or equal to 0, this value should be greater than or equal to d lambda star u, where lambda star is the optimal dual for VB, right? Okay. So when the right-hand side equals to B, let's assume lambda star is the optimal dual value. Okay. Yeah.
So if lambda star is the optimal dual,
Yeah.
it's because in the past we were always grabbing the smallest lambda, or am I conflating that with the eigen? I'm conflating with the eigenvalue.
Okay. Yeah, that's fine. So here, since you are maximizing over all the lambda greater than or equal to 0, right? It must be greater than or equal to a particular lambda star, I find. Right? The lambda star is from the optimal dual for VB here. Okay. So what is this part here? It is nothing but minimize x C transpose x plus lambda star gx minus u, right? So here I'm just plugging into lambda and solve this optimization problem, right? Now let's rewrite this problem a little bit. There should be a lambda transpose, but I will neglect that to simplify notation a little bit. Then okay, so here I did nothing but I changed this u by b, and then I need to add it back, right? This is just nothing but a simple algebra. Okay, so now here you are solving a minimization problem over x, right? And this part is independent of x, right? So then you don't need to worry about that. Then what is this part? Right, so you are minimizing x, C transpose x, where lambda star is the optimal dual when u equals to b, right? So this is essentially the Lagrangian dual when v equals to b, right? So therefore this part, because of strong duality, this part is nothing but VB, right? Because you are giving the optimal dual at when u equals to b, right? The right-hand side is b. So then if you rewrite this is essentially VB minus lambda star u minus b, right? So that's the end of the proof where you have VU here, and then you have greater than or equal to, and the right-hand side is VB minus lambda star u minus b. Right, so that shows minus lambda star is a subgradient of the value function. Yeah.
So for finding lambda star, when we do that, is that the same as we find lambda star by maximizing the dual first, right?
Yeah. So you can assume lambda star is given to you by solving this particular problem, right? After you solve this problem using interior point method, you got the dual from this problem, right? It's just lambda star is the optimal dual at a given value of b. Okay. Yeah. So this part completes this minus lambda star is a subgradient, right? Okay. So that's probably the most important thing I want to show, because this is something even more general than range reduction, right? You can use this as a subgradient of a value function. in the future. Okay, so with this, then let me neglect the last part of the proof. You can read it by yourself. The idea is once you show essentially this part, the blue line is your value function, the green line is a subgradient we just derived, right? And then you can show that my argument is true because this green line underestimate the blue line, and then if you go further away from this particular value of bj, at this point it will go over the upper bound, and you don't care about this part of the range. That's sort of the argument here. But then the main trick is you need to show the dual is a subgradient of the value function. Okay. Yeah. Now you can read about the detailed proof after the class if you are curious. Then I still have around 15 minutes that should be roughly enough to show you the other bound tightening methods, right? So now you can sit back and relax because all the other bound tightening methods are much easier to understand, okay? So then the feasibility-based bound tightening refers to, tightening variable bounds after some other variable bounds have changed, okay? Just to give you a few examples, if you have xj equals to xi raised to the power of the third, and then you know the bounds of xi, right? Then you can tighten the bounds of xj by intersecting the bounds of xi raised to the power of third with original bounds of xj, right? This is just a simple replacement of variables. You can tighten the variable bounds. And vice versa, if you want to tighten the variable bounds of xi, you can take the xj raised to the power of 1/3 to tighten that, right? Okay. So let's see. Here's another example of feasibility bound tightening. This is especially useful for problems that involve bilinear terms, where you have xk equals to xi times xj, right? So let's suppose we have variable bounds for xi, xj, and xk, right? The lower bound xi, xj equals to 1 can imply a tighter lower bound for xk, right? Because here, the lower bound of xk is 0, right? But the lower bound for xi and xj are 1, right? So therefore, the lower bound for xk can be tightened from 0 to 1 just by simple plugging into the bounds, right? And similarly, you can tighten the upper bounds by doing a simple division of the two variables, right? So when McCormick relaxation is used, then you can use this trick to tighten variable bounds, okay? It should be pretty easy to understand. Now, let's talk about another thing for feasibility-based bound tightening for linear functions. So suppose you have an auxiliary variable xk or any xk variable where you have this term in your convex relaxation, where xk can be written as a linear combination of a bunch of other variables, right? Where k is greater than n, okay? Now, let's write this constraint in two ways, where you could write xk is less than equal to this right-hand side and xk greater than equal to the right-hand side, okay? So here we define a set J plus where the element J is in the set J plus if this coefficient Aj is greater than 0, okay? And then the J indices is in the set J minus if Aj is less than 0, okay? So now you have a summation over the negative coefficients and then the positive coefficients here, right? Now, as you can see, if the indices is negative, right? And then you want to derive a lower bound on xk. Then you should choose the upper bound on this particular variable, right? Because you want to derive a lower bound, and then the coefficient is a negative number, right? And then you will choose the upper bound. Otherwise, if this coefficient is a positive number, then you should choose the lower bound of this particular variable in order to derive a lower bound on xk, right? And similarly, if you want to derive an upper bound, it's the other way around. Right? So this is simple algebra, right? If you are a bit confused by the notation, just pick a small problem and then try to plug in some numbers to see if this is true. Okay. Now, if you have some explicit variable on xk, then they will imply some potentially tighter bounds on all the other variables. You could use this formula, right? All these are very simple middle school algebra, and I will not spend too much time on it. Although the notation can be quite complicated, but if you sit down, go over all the notations, you will see this is true. Okay. We have a small exercise you can quickly practice that. Okay. Now, as you can imagine, if you can use feasibility-based bound tightening to tighten all the variable bounds, right? Some of the variable bounds change, all the related variable bounds may change, right? And then you can come back to tighten these variable bounds again. It may enter an infinite loop, right? Okay. So then this procedure does not terminate unless the tolerances or some iteration limits are imposed, because you could iteratively update the variable bounds, right? Some variable bounds propagating to other variable bounds, and then that further propagate back, maybe, right? You could keep iterate. It may not converge, but then typically what people do is to set a finite number iterations for feasibility-based bound tightening. Okay, the other idea is even simpler. It is called optimality-based bound tightening. Okay, now suppose we have some variables xi. We have n variables. We want to update the upper bound and the lower bound of these variables. Then you could solve an optimization problem to do that. Right? How do you get the lower bound of a particular variable xi? You could solve a minimization problem where x is in the feasible region. Let's assume S denotes the feasible region of the original problem. And then we add another constraint saying C transpose x less than or equal to U. Right? Remember, U denotes the current upper bound. Right? You are not interested in any solution that are even worse than the upper bound. Right? So you are only interested in solutions where the objective is less than or equal to U and x being feasible. Right? By solving this particular optimization problem, you can get a lower bound for a variable xi. And similarly, solving a maximization problem will give you an upper bound of xi. Right? It is very, very easy to think about. So if you want to get the lower bound and the upper bound on all the variables, you need to solve 2n optimization problems, right? Which can be quite expensive. Right? So remember, in the previous case, in feasibility bound tightening, these are just some arithmetic steps, right? Doing some division, addition, and so forth. But this optimality-based bound tightening will solve 2 times n optimization problems, and it's much more expensive, right? The other thing is typically people will not use the original constraint S, right? So we will not use the feasible region of the original problem. We can replace S by its convex relaxation. Right? Because if you use the original problem, this bound tightening problem is as difficult as the original problem, right? Yeah.
When we do the 2n optimization problems, are we holding the other variables constant and we're only varying one of them at a time? And then we're seeing what that min is or what that max is?
Yeah, that's a good point. So yeah, so you are optimizing all the variables x, right? But in the objective, you are optimizing one single variable, right?
Okay.
So you are optimizing the bounds for each variable separately, but then the variable bounds depend on all the other variables, right? Therefore, in the constraints, you do not fix all the other variables. They can change.
So how is, I understand how that's a separate problem than just solving the original,
Yeah,
the original optimization problem.
yeah,
Right, because if we're already gonna be changing all the variables at the same time,
yeah.
just to give a lower bound, wouldn't the lower bound already be the new solution
The lower bound already being a new solution or what?
of the original optimization problem?
Oh, I see, yeah. So the original problem is C transpose X. Here you are just optimizing variable bounds. So therefore, what I said is you will not use the constraint. So this S represents the constraints of the original problem, right? Then it is too difficult to solve. You can replace S by a convex relaxation of the original problem.
Okay,
Yeah,
so
yeah.
we're solving slightly different.
Yeah, slightly different problem. Otherwise, the variable bound tightening is as difficult as the original problem.
Yeah.
Right. So that's why I said we can replace S by its convex relaxation. Right. This is like theoretically what your upper bound and lower bound for each variable is. Right. But then since you cannot solve that, you solve a relaxed version of that problem. Okay.
That makes sense.
Yeah. Okay, so then, as I said, you could, a practical approach is to use a convex relaxation, assume this is a linear programming relaxation of the original problem, then you could solve this relaxed version to get the upper bound and lower bound instead of solving the problem with the original constraints. Okay. Yeah, so what are the pros and cons for OBBT compared with FBBT, right? So this is another demonstration of no free lunch theorem, right? The advantage is that OBBT is looking at all the variables at the same time, right? In the all the constraints at the same time, at least in the convex relaxation, and try to find the upper bound and lower bound for each of the variables. And FBBT is looking at each constraint separately. Right? So remember, in FBBT, if you look at this approach, right? So it is looking at a particular constraint rather than looking at all the constraints altogether, right? So therefore, OBBT will typically give you tighter variable bounds. But it requires solving 2 times n linear programs, right? If your relaxation is linear programs, then you need to solve 2 times n linear programs. So typically it's more expensive than FBBT. And one heuristic people use in branch and bound method is to limit OBBT's use only at the root node or only at the first few nodes, right? Then for the other nodes, you will only use FBBT. Okay. Now the final approach we will talk about is approach called probing. Okay, so it is a technique that was originally proposed to solve mixed integer linear programming problems, but it has been extended to solve mixed integer nonlinear programming problem or non-convex nonlinear programming problem. Yeah. So the idea of probing is the following: it will tentatively fix some binary variables and then propagate those fixing over the constraints to see what happens. Okay, so if you can find some conflict, that means you cannot fix a binary variable at those values. Okay, so let me show you an example and then discuss this again. So this is a very simple mixed integer linear programming problem with 2 binary variables, 2 constraints. Again, the idea is we will tentatively fix some of the binary variables. So let's fix x1 to 0 and see what happens. Right? So if we fix x1 to 0, we get the rest of the constraint will be reduced to these 2 constraints. Right? Clearly, this is infeasible, right? Because you have x2 less than equal to 10 over 3 and x2 greater than equal to 8, right? So it is clearly an infeasible problem. Therefore, you cannot fix x1 to 0, right? Otherwise, the problem will be infeasible. So now let's tentatively fix x1 to 1. Right? What will happen is we have x2 less than equal to 8 and x2 greater than equal to 1. This leads to x2 equals to 1 being the only feasible solution. Right? So therefore, through probing, you can already fix the value of some of the variables, or at least remove some assignment of the binary variables. Okay. So the idea is different from branch and bound is because you are not solving linear, you are not even looking at the objective, you are not even solving linear programming. Right? You are just tentatively fix some of the binary variables and propagate that through the constraints and see what happens. Right? That's the idea. So how does probing work in global optimization? Okay. So here we don't have binary variables, right? Let's suppose we apply it to some continuous variables. Then the idea is we can use probing to tighten variable bounds. Suppose we adjust the upper bound of variable xi to a given value, right? Where this value is even tighter than the current variable bounds, right? We don't even care this new variable bounds ui prime is valid or not, right? So let's just tentatively tighten the variable bounds and see what happens, right? Then we apply feasibility bound tightening, right? So if the feasibility-based bound tightening result in infeasibility, or the lower bound is on this particular problem exceed the cutoff value, then it indicates that there is no optimal solution within this particular interval, right? So then you can adjust the variable bounds to ui prime and u, right? So that means you tentatively tighten the variable bounds, and then you find out at this tightened variable bounds, there is no way you can find interesting values, right? Meaning that they are either infeasible or they are suboptimal. Right? So then you can get rid of this particular region. It's similar to the mixed integer linear programming case. You fix the value of the variable, then you got some very uninteresting result, meaning that makes the problem infeasible. Then you can just fix those binary variable. Right? And same logic, you can apply it to the lower bound. Right? So the idea of probing is that you can use these schemes to significantly narrow the variable bounds. Now, if you want to use global optimization solvers, which one you could use? Right? Again, Baron is one of the earliest global optimization solvers developed by Professor Sachnidis, who is a chemical engineer. And the second solver, Antigone, was developed by Professor Fluda's group from Princeton. So if you remember one of the seminar speakers we had in the previous semester, Professor Ruth Meissner, she's the main developer of Antigone when she was a PhD student at Princeton, right? So basically she single-handedly developed an optimization solver during her PhD, okay? Then there are also other global optimization solvers, like Skip is an open source global optimization solvers. Then now I should probably also add Groovy because it can also solve general mixed integer linear programs now. Again, if you are interested in the performance of those solvers, you can check the Mittelman benchmark on mixed integer nonlinear programming problems. Okay, and then these are the references. Especially if you are interested in bound tightening, I would refer you to this particular tutorial. Okay. Any questions? All right. So again, I spent a little bit time on deriving this subgradient theorem, right? Because that is a sort of a very general theorem you could use for your future research. And all the other range reduction methods are quite easy to understand. You only need to understand interval arithmetic and simple optimization problems.